All right. Today, continuing on with the same idea, just seeing more than what we would have considered linear equations. So just a step more challenging in the solving process. Today, we're going to focus on the quadratic form. Quadratic form, the two different types of ways that we would look at this via factoring and square rooting. And we have several different ways of solving quadratics. When we're doing trig equations, those are the two that we will utilize, factoring or the process of square rooting, kind of how it is set up. All right, so jumping into our first example here, how do I know that I have to consider to factor something? As I scan through my equation, I see multiple trig functions, but are not like terms because I have one of them that is squared and one of them that is to the first. I can't combine those because it'd be like an x squared and an x. And so that tells me that I need to do some sort of factoring. If it helps you, especially as we are getting used to this, rewrite it, take out the trig function and replace it with like a. So you can see what that would look like as just a quadratic minus the distraction of trig. So if I did that, this would be like 2a squared plus a minus 1. Is that something that we can factor? Absolutely. Okay. This is where you have to remember your method for factoring, whatever that is. Be good at it. And if it is slide and divide, don't forget your divide part. Okay. So we factor, but instead of it being an a, it's a cosine of x. So as I go to fill in my first term, I'm a guess and checker. I would find two numbers who multiply together and give me 2, which would be 2 and 1. So 2 cosine of x and 1 cosine of x are my factors of 2 cosine squared. My factors of 1 are 1 and 1. And I just have to figure out where to put in my positives and negatives so that when I do my outsides and my insides, they'll add up to give me a positive 1 cosine of x. So that would be positive 2, negative 1 gives me a positive 1 cosine of x. Through whatever your method is, we should get to this. As far as order, remember that with quadratics, order does not matter when you factor this, signs do. So if I put the 2 cosine of x second, it should go also with the negative 1. Wherever that one ended up, it should be the 2 cosine of x minus 1. And then just like we would have had we been over here factoring solving for a, once we have it factored, we set each parentheses equal to 0, and it's now basically like 2 equations from yesterday. Okay, so the only new layer to this is getting to this point via factoring. Now I just set each of those equal to 0. And solve. So as we solve, let's go ahead and go with the 2 cosine of x minus 1 equation first. So I would add 1, divide by 2. Think through my all students take calc. Cosine is positive in quadrants 1 and 4. So from this, we would find answers from quadrants 1 and 4. We are only going from 0 to 2 pi, so I don't have to add in my plus 2 and pi. Okay. And my reference angle that gives me a cosine of 1/2, what is that? Pi over 3. And pi over 3 in quadrant 1 is pi over 3. What's the pi over 3 in quadrant 4? Very good, 5 pi over 3. Okay. And then we go to our other side and say, okay, cosine plus 1 equals 0, which means cosine of x equals negative 1. And we saw this on our worksheet last night, but we didn't really get much of a chance to talk about it in class. So let's take a second. When we're looking at a sine or a cosine that is like a 1 or a negative 1 or a 0, remember that that came from an axis. And there are some others that come from an axis as well. So then we have to think through this whole thing, right? 0, pi over 2, pi, 3 pi over 2, each of our ordered pairs. And we're looking for cosine, cosine being the first number in each of those ordered pairs, and we're looking for where it equals -1. So no, here is where we're looking. My answer would be that angle, which is pi. And so what we're going to find out today is that we're going to get a different amount of answers than we were. Yesterday we saw very frequently 2 answers, right? Sometimes 1, most often 2. Today, because we're factoring, you can have anywhere from none, which can happen, up to like 6, I don't know, a lot of answers. Okay, so questions. All right, let's see some other variations. This one is very similar to the one we just did, so I'm going to let you try this one a little bit ahead of me here. Yes. Yep, so start with taking your 2 times 1 and then factor from there. Nope, just take your 2 times 1 and then factor it like it says x squared minus 3x plus 2. And then you have to go back and divide. So our original first number was 2, so now I'm going to go back and divide each of those by 2. Ooh, but factors of 2 are not 2 and 3. Factors of 2 are 2 and 1. All right, we might need to brush up on our factoring method, okay? I shouldn't even encourage this, but I will go through a review of slide and divide. Is it clear enough that I don't like this method because we're not good at it? But I'm not about to change that right now. So if this is what you need, slide, we multiply. I factor. Factors of 2 are 2 and 1. To get a -3, they would both be negative. And then I have to go back and divide because it's slide and divide, right? And I divide everything by that original front number. If it simplifies down into a whole number, great. If it does not, I simplify the fraction, but then I also multiply by the denominator or slide it out front. All of this is very non-mathematically based. Yes.
Do you have to do that because you're like if you end up like equaling it to 0?
No, you don't have to. You're saying slide the 2 out front.
Yeah, because you're still getting the same thing.
If you are solving an equation, it will not change your answer in the end.
Okay.
Yes. I absolutely can go through the grouping method, and I actually like that one better. So our grouping method, and we'll just go ahead and do that on this one, it breaks your middle term into 2. And so we think about, let's see. Breaking -3 sine of x into 2 numbers that add up to -3, whose product would be the same as 2 times 1. So 2 times 1 is 2. And breaking the -3 into 2 numbers that would give us that would be like 2 and 1. And when I do that break the middle one, it is now to the method of factor by grouping. And so I group the first 2, I group the last 2, and I take out my GCF. My GCF for this first term would be 2 sine of x, and if I factor a 2 sine of x out of each of those, I get a sine of x and a minus 1. And then here I need to match this, and right now my signs are exactly opposite, so the GCF that I would factor out of that would be like a negative 1. If I factor a negative 1 out of each of this, it would be sine of x minus 1. And then you factor out your GCF of that sine of x minus 1. Both of these terms have a sine of x minus 1. So that thing that matched is your GCF, and I can factor that out, leaving me with what was left over, 2 sine of x minus 1. If you notice, they are the same answer. You like this one better? I do too. All right. Either way, we get to this here, and again, we are back to our problems from yesterday. I said each of these equal to 0. Solve for my trig function. So again, if it's a sine or a cosine and it's equaling 1 or negative 1 or 0, it's going to be from an axis. Which angle has a sine value of 1? Pi over 2. So our answer from this would be pi over 2. Over here, we would continue to solve. Add 1, divide by 2. Sine of x is positive in quadrants 1 and 2. So from this side, I should get an answer in quadrant 1 and quadrant 2. The reference angle that gives us a sine value of 1/2. Pi over 6. And then the pi over 6 that puts us into quadrant 2. 5 pi over 6. Questions? All right. This is Miss Yonda. Hi. Shh. No, notes. Oh, okay. Is it okay if we wait till the end of class? Perfect, thanks. All right. Difference between this one and the one we saw on the last page. We have a squared, right? So it tells us it's a quadratic, but there's not another term, right? So again, think about this without the distraction of the sign. This would be like 4a squared minus 1. We can solve that. We can solve that with factoring, but we can also solve it with square rooting, okay? So you have two options. If you looked at this and immediately saw like a difference of 2 squares, factor it that way. Great. If you saw this and you thought square rooting, go that route. You just have to be careful with the square rooting part of it. So I'm going to go that route so we can talk about this. If I just have a sine squared and no other sign, I can solve by square rooting. At this point, it looks a little weird because 1/4 is not a unit circle number, but we're not done yet, right? It still says sine squared, and that's also not on my unit circle. And so I would square root both sides. And here's where square rooting can hurt us. When I square root, what do I need to remember about my answer? Positive and negative, right? So don't forget your plus or minus. If you are somebody who has frequently forgot your plus or minus over the years, you know that person that always has to have plus or minus written on their test, right? Factor by difference of squares, and you will not ever lose any of your answers. But if you are good at remembering the plus or minus, you're fine going the route of square rooting. The square root of a fraction can be broken into the square root of the top over the square root of the bottom. These both happen to be perfect squares. So I can go ahead and just square root each of those numbers. The square root of 1 is 1. The square root of 4 is 2, and that now is looking familiar. But here's what's very unique is I have both plus and minus. And what does that mean about my answer? Well, when it's positive, sine is positive in quadrants 1 and 2, but I also get the negative, which means I get answers from all 4 quadrants. So once I figure out what that reference angle is, I list that reference angle for all 4 quadrants because it is positive and negative, okay? And I think we just did this one again. I don't know why we do sine of 1/2 equaling 1/2 all the time in here, but it's still pi over 6, right? And then pi over 6 in every quadrant. So pi over 6, 5, pi over 6, 7, pi over 6, 11, pi over 6. Questions? All right. Try this one on your own, very similar to the one we just did. You might get hung up a little bit on the solving part of it, and I can help with that. Yes. If you take out a GCF, you can. Oh, you know you can't. It's because, yeah.
Because it has to be a.
Right, right. Yeah, no, this one's not going to work as nicely. You could make it work. It's not going to work as nicely to do your difference of 2 squares. Sure. All right. Did you notice the slight difference in our solving on this one? It wasn't a nice square root, was it? We had to do a little bit of work. Well, 2 over 4 does simplify to 1/2. You may not want to simplify it because I'm going to show you if we go back when I did my square rooting. But when I square root this, for again, as always, I get plus or minus. But as we look at the square root of this, the square root of 1 over the square root of 2, 1 square roots nicely, but 2 does not. And so we would have to look at rationalizing, right? And that's where it gets into being a number that we, again, expect to see on our unit circle because we get the square root of 2 over 2. You can see that from here, but guys, look, what if I had gone and square rooted here? If I don't simplify that fraction, it actually kind of squares a little faster because that's the square root of 2 over 2, which is what we got. So anyway, what is that reference angle that gives us an answer of square root of 2 over 2? Pi over 4. And again, positive and negative means I'm getting answers from all 4 quadrants. So we are now looking for the pi over 4. That puts us into all 4 quadrants. 3 pi over 4, 5 pi over 4, 7 pi over 4. Any questions? Okay. Mixed trig functions. We're going to see this a couple different ways. Monday, we'll look at this through a different lens. Right now, we're going to see this where all terms have a trig function, and we have more than one trig function in our problem. 2 very important things I want you to get out of this. Again, get rid of the distraction. We're looking at like a right? So in order to solve this, I need to, again, especially because it's a quadratic, need to get everything onto the same side. So my first move right now, follow along with my solving here, is I'm going to subtract 3 tangent x. These are not like terms, right? Because this has an x squared attached to it. I am just moving everything to be on the same side of my equation, which would be the left-hand side by subtracting 3 tangent x. So I have tangent x sine squared x minus 3 tangent x. Again, if I were to like write this without our distraction here, what would you tell me to do? GCF, right? We have a GCF. Remember that when I factor out a GCF, it doesn't go away. It's just pulling it out front and saying, hey, all of the terms had this. It's part of this equation, but I can separate it out because they all had it. So I can factor out a tangent of x from each of my terms. And again, once I have factored completely, I can set each part equal to 0. Okay, so that's the first important thing I want you to get out of this example is a GCF. When you start seeing mixed trig functions today, think GCF. Get them on the same side, factor out the one they had in common. Okay, so set then each part equal to 0. Tangent's always the tricky one because if it had said tangent of x equals 1, that actually isn't a quadrant, isn't it? Pi over 4 gives us a tangent value of 1. Tangent equaling 0 is actually on an axis though, and you have to do a little bit of work because it's not just scanning through your ordered pairs, is it? But it's taking your sine value over your cosine value. So like here at 0, our sine value over our cosine value would be 0 over 1, and thinking about what that simplifies to. Well, it simplifies to 0, and so tangent of x will equal 0 when our angle is 0. And I think through each of those ordered pairs, and I say, okay, if I were to take my sine value over my cosine value, does it simplify down to 0? At pi over 2? No, that's undefined, right? And then the other place that it will simplify down to 0 would be here, right? Because again, that'd be 0 over -1. 0 over -1 is 0, what we're trying to get. And this angle is pi. It did say on this one to find all solutions. So I'm going to back up here and say that we add. So those were the 2 answers I got. Do you remember the little trick to the tangent though? For all solutions? N pi. Every other one, 2n pi, but it only has a period of pi, so we just say n pi. That's unique to tangent and cotangent. Okay, the second thing I want you to get out of this example is what's going to happen with our other problem. It should start confusing you at about this point right here when I go to square root this and I get that the sine of x equals plus or minus the square root of 3, and I am not finding something on my unit circle where sine of x equals the square root of 3. Okay, now this one's a little bit tricky. Usually it's a little more obvious, like a 4 or a 2. But remember that sine and cosine actually only have a range of -1 to 1, and this is like 1.5. It does not exist on its range of -1 to 1. So in factoring, this can happen more often than we like, but that we'll run into the end of a problem where maybe one side or the other or both don't produce answers for us, and that's okay. So like from this one, we would say that we are not getting any additional answers, but our answer is not no solution. I just want to make this very clear. We have answers to this problem, don't we? We have actually 2 answers to this problem. And so sometimes people try to tell me that the answers are 0 plus n pi, pi plus n pi, and no solution. That doesn't make sense, right? So if I were going to go off to the side and list my answers, it would just be these 2. All this is saying is this added nothing additional to that list. Now, had that happened on both of my possibilities, then my answer could be no solution if both of them did not produce any solutions. But if I have a solution, no solution is not an answer. Questions? All right. I think this is our last example today. Reciprocals. Secant squared x equals, -2 equals 0, and we're going to solve this one from 0 to 2 pi. You can again treat this a little bit differently in the middle, but we should get to the same place at the end. First of all, just solve for your trig function. So I would get secant squared x equals 2. I like to reciprocal at this point. Okay, so now I'm going to take the reciprocal. The reciprocal of secant squared would be cosine squared. The reciprocal of 2 would be 1/2. And you must reciprocal both sides, right? And then we can proceed. Continuing to solve, cosine squared, I would square root. When I square root, I would put plus or minus on my answer. You may or may not remember what this will simplify to. If you do not, come off to the side and show your work to rationalize, and we get to the square root of 2 over 2. The plus or minus tells me we have how many answers? 4 answers on this one, right? Cosine is positive in 1 and 4. It is negative in 2 and 3, which means we get answers from all 4 quadrants. And what is that reference angle? Pi over 4. So answers of pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Questions you guys have for me?